off in some time. இப்போ ஸ்ட்ரீம் ஆகும் பாரு.
Hello. We also haven't started. You can. Hello. Yeah. Thanks. Thanks.
தரணி வந்துருச்சா? ஓகே. Bro, you logged in here, bro? Okay, cool. லாகின் பண்ணிட்டு இந்த லைவ் அப்படியே போட்டு இதில் ரீஸ்ட்ரீம் தான் ப்ரோ பண்ணணும். அது தட் இஸ் ஆல் வி கேன் டூ.
என்னாச்சு? போகுது. அதை ப்ளே பண்ணிவிடுங்க. ஓகேவா?
லூப் ஆகிட்டு இருக்குது பக்கத்தில்.
அதோட பிரச்சனை இல்லைங்க, சவுண்டு
லூப் ஆகிட்டு இருக்குது.
I need to log in and.
Yeah. Here, bro. Come. Log in.
அந்த லிங்க்கை மட்டும் எனக்கு அனுப்பிச்சுடுறேன். இப்போ லைவ் ஆயிடுச்சுல, இப்போ அந்த லிங்க்கை மட்டும் எனக்கு அனுப்பிச்சுடுறேன். அவ்வளோ.
டே 3 பார்ட்டிசிபென்ட் தானா?
ஒன்று கால் பண்ணானுங்க. Said will come in 30 minutes. வேறு ஏதாச்சும்?
ப்ரோ தட்ஸ் ஆல்.
ஷுவரா?
செக்கே பண்ணலையா யாரும் அந்த லிஸ்ட்டை?
செக் பண்ணுறாங்க, திருப்பி சொல்கிறாங்க. அவருக்கே RSVP லிங்க் வந்து அவரால் இது he can see whoever are registered, not the back end detail.
இதெல்லாம் உனக்கு முன்னையே காட்டணும் ப்ரோ. கடைசி நேரத்தில் ஸ்ட்ரீம் பண்ணணும்.
இப்போதைக்கு மியூட் பண்ணி வச்சுக்கலாமா?
யா ஹலோ. Hi guys, am I audible?
ஓகே
Yeah?
இதுக்கு அந்த பாஸ்போர்ட் ஆஃபீஸ்ல கால் பண்ணாங்க, அவங்களுக்கு மெயில் ஐடி
அவங்க ரெண்டு பேர்த்துக்குமா? பிரகாஷ் சார் இது சொனாலிக்கு வேணும்.
சொனாலி நான் சொனாலி கூப்பிட்டு கேட்டேன், அவர் தூங்க போயிட்டாரு.
தூங்க போயிட்டாரா?
எனக்கு மெயில் ஐடி சொல்லுங்க, அவரோட மெயில் ஐடி தெரியுமா தெரியாது உங்களுக்கு?
அவரோட மெயில் ஐடி எனக்கு எப்படா தெரியும்?
ப்ரோ அப்போ என்ன ஏர்லியாக போஸ்ட் ஆரம்பிச்சிருக்கோம்.
ஹலோ, யூடியூப்பில் சவுண்ட் வருதுல்ல? ஹலோ ஹலோ, ஓகே குட். ஹலோ,
அவ்வளோதான் ப்ரோ.
ஸ்க்ரீன் ஷேர் ஆகுதா இல்லையா ப்ரோ? How to check if the screen is being shared or not here?
ப்ரோ நான் பார்த்தேன்.
Huh?
No, you can log in. No, it's not shared, bro. If you're sharing.
Okay.
Yeah, it is showing that screen. என்ன screen இது?
நான் ஆடியோவையும் லூப் பண்ணிட்டேன். ஸோ
Someone can log in and check, bro. Anybody that RSVP into that thing.
ஓகே, இட்ஸ் ஆடியோ ஷுட் பி ஒர்க்கிங். அதை மட்டும் செக் பண்ணிக்கோங்க.
Somebody need to go and check. Who to check? No, Linux Foundation.
ப்ரோ நீங்கள் ஆர்எஸ்விபி பண்ணிருக்கீங்களா? கேன் யூ லாகின் அண்ட் செக் இஃப் யூ கேன் ஹியர் த ஆடியோ? ப்ரோ உங்களை ஸ்க்ரீனில் வேறு தான் நீங்கள் மாற்றி விட்டிங்கன்னா ஐ குட் ND8 போட்டு. யா ஓகே ப்ரோ நீங்கள் உங்கள் மைக்கை மாட்டிக்கோங்க. பேசிக்கலி வி காட் ஆன்லைன் ஆடியன்ஸ். யூடியூப்பில் ஆடியோ ஆடிபிளாக இருக்கான். லினக்ஸ் ஃபவுண்டேஷன் மட்டும் ஓகே சொல்லிட்டாங்கன்னா வி ஆர் குட் டு கோ. ஷர்ட்டுக்குள்ளே விட்டுக்கோங்க. All good, also screen is good. Yeah bro, they're all good. Linux Foundation is good.
Audio is also.
Yeah. Bro, you could start. And I'm taking questions from YouTube also. So. Bro, yeah. 2 minutes. We start in another 5 minutes. Yeah, we got a lot of online audience. Bro, that guy 30 minutes he said. Yeah. Okay. Bro, you can sit there. You can sit there, bro. You have your mic, right? Yeah. Okay, you can start talking. Sit, bro. Yeah, all good. Yeah, bro. யூடியூப்ல யாரோ ஆடியோ மட்டும் கேட்டுக்கோங்க.
கேட்டுதான் இருக்கு.
நல்லா இருக்குல்ல? தரணி என்ன பண்ணுறான்னு கேளு. எல்லாத்துலேயும் ஃபயர் பண்ணிட்டாங்களா இதை? ப்ரோ ஆல்ரெடி ப்ரோ வி கேன் ஸ்டார்ட் பண்ணலாம்ல?
அவ்வளோதான். நீங்கள் பாட்டு யூ கேன் கோ ப்ரோ. அவங்க 2 பேர் தானா? வேறு யாரும் காண்டாக்ட் பண்ணால் போய் ஆடப் ஆகிக்கலாம். தென் வி கேன் ஜஸ்ட்
இல்லை ஆன்லைனில் இங்கே வந்திருக்கு பாரு. யூடியூப்பில் எத்தனை பேர் வாட்சிங்க?
16.
Okay, it will start. As we start, it will grow. எல்லா குரூப்லேயும் பண்ணிட்டீங்களா? ஓகே கூல் ப்ரோ, யூ கேன் ஸ்டார்ட். அந்த டோரை லாக் பண்ணிடுங்க. வில் ஸ்டார்ட். லெட் see how this goes. இல்லைடா, கோப்ரோ ப்ராப்ளம் இல்லை, இங்கே இருக்குது, அதெல்லாம் ப்ராப்ளம் இல்லை. ப்ரோ நீங்கள் நின்றுட்டு பேசுகிற மாதிரி இருந்ததுன்னா ப்ரோ நீங்கள் அவரோட இதை அட்ஜஸ்ட் பண்ணிக்கணும். இல்லை if you want zoomed one of Manoj's view நாலும் I can give you one like this, but that's not good bro. We'll go for this. Bro அது மறுபடியும் adjust பண்ணுங்க. Bro you can start bro.
இது OBS இல்லை, இது கேமரா ஹப்னு, இது தனி.
அது தனி.
இது OBS.
இது OBS.
Start up.
Yeah.
Audio now.
All good.
So good morning. Thank you so much for coming. So basically, it's about Zephyr event, Linux Foundation. But we are working together with Linux Foundation to make the event happen. And myself, I am the contributor to the project. I am an open source contributor. I am hosting this event with my cousin here in India. Myself, actually, I am based in Malaysia. So I run a consultancy firm for doing embedded systems. So just a little bit about myself. I run the embedded system, firmware development, hardware development, all this kind of like a design house. And then I started contributing to Zephyr, and I came to a point that hey, I can also contribute, because it was like pretty cool at the time the project was started, open source and all this thing. And
இந்த
And
camp
then I
தான்
decided
idea.
I'll become the ambassador also because as a techie we like to talk about techie things. So Zephyr was a cool fit to me because I
Audio.
was able to talk
Caller
about
audio,
the
correct.
inner working and technical stuff.
Caller audio.
So this some boring stuff.
Bro, உங்கள் மைக் கொஞ்சம் வெளியே எடுத்துருங்க. Your mic is inside. Bring it outside. Okay, good. Yeah.
Okay, so we're good.
Yeah, we're good.
So these are some kind of works we are doing, schematic. If anybody is into embedded system will know, we make schematic, we make PCB, and then we have this 3D where we manufacture board.
போலாம் சேர் எடுத்து போட்டு உட்காந்து கவனிப்போம்.
And this is some contact setting. So just before we went into the biggest project we have done so far with Zephyr specifically, it's like a fully automated warehouse setting in Malaysia. So basically these are all mobile robots. They can dispatch items, they can take and put items anywhere you want in a 3D space. And this entire stack is powered by Zephyr RTOS. So you can think about motion controller, Wi-Fi, and all these things. That's later we forgot the
Yeah. Labs is done. Okay.
So I'll just get into so I hope I've set up the contacts, no questions or this who am I and what I'm doing and so forth. So now we jump into Zephyr itself, what Zephyr is and how Zephyr itself want to portray to developers, how to take it, introduce Zephyr to some people, developers basically. So where are real-time OS are being used? I hope everyone know what is RTOS here. So RTOS, as we know, everywhere it's being used, industrial IoT, as now we see machines are getting connected to internet and all of these things. So that's where the landscape of RTOS is becoming different because connectivity is affecting in a lot of ways. You need to get into internet. And all this common thing, asset tracking, wearables, automotive, healthcare, worker safety. And the key point that any RTOS need to be in a way that you want to use it in 2023 is it should be small enough that it can go into a very small device like 8 KB flash, 5 KB RAM, but yet it can be scalable. Meaning if you want some complex application like a watch, it should be able to get that as well. So that's the point where Zephyr is in point where it is covering this both aspect. And it has to be flexible, meaning flexible in terms that you want to support lots of SoC. SoCs means you want to support ARM, Intel x86, RISC-V, and so forth, Extensa and all these things. So that is also possible, and it's already proven in the market at the moment. And then you want to be secure, like we saw, we want to be in healthcare industry and all this thing. So you need to be by design open in nature and has to be secure that it's auditable. So that's the difference between if you're talking about like 5 years ago, 10 years ago, you go into like key RTOS or whatsoever. Those are all closed source. There's no any auditability and all this thing. So this, since the code is open, people are doing CD report, complaining and fixing bugs and so forth. And of course, a big aspect of it is Apache 2.0. So for one example is we take Zephyr code and we make our own product, we make modification, and we can without any issues sell the product because it's Apache 2.0. So you don't have any limitation on that side. And the bigger advantage will be the ecosystem itself. Like now we are running events, and because we have this common team Zephyr, all the people come together and you can get support from the community and so forth. And another thing is, like if you are using very common, very famous SoC in place like STM32 and XP and all this thing, the vendor itself already contributed a decent portion of it, and the vendor is committed to support it. So here's the thing. when people ask about, okay, Zephyr OS, so what is OS different with RTOS? It is not commonly said that it is lightweight enough that it mimics Linux, but it's not Linux. Wherever Linux can't run, you can run Zephyr, and it mimics the style and working of Linux and how you develop application. And it has to be portable. So we saw earlier on the slide, it supports 400 boards. Any types of SoCs are supported without breaking. So if you have worked on FreeRTOS, you might argue that okay, FreeRTOS also supports all the board. But the point is, FreeRTOS doesn't have any abstraction layer that Linux has, like board layer and anything on top of it. Here, just say you are swapping a board, your application code can be same 100%. Meaning you are not making any single changes on top of any API layer, whatever you are using Zephyr. So that's the biggest differentiation you can think of in terms of RTOS, any other RTOS. And from the day itself, because connectivity is a big thing, Zephyr has its own way of abstracting network stack. Why its own way of network stack? Because we saw the point earlier, it has to be super lightweight and it has to be in a way portable. So that's how we handle the application layer and talk to Zephyr OS network stack using the R. And the last point is this slide is developer friendly. So any RTOS, if you want to work on it, you want some kind of debugging capability. So yes, you can do that in other RTOS also, but it doesn't come out of box. So in Zephyr, maybe you need a tracing, you need a logging, you need a good logging. You don't have to go and discover, oh, what logging I want to use. There are some sets of logging, tracing, debugging and all this thing already in the ecosystem. So just say the board you want to use, just say it's ESP32. If that board is supported, by day one, it already have logging, tracing, debugging all implemented. You can just take and use. And it's not specific to the particular board, it is specific, it is for the ecosystem. So you learn it once, you can apply in any boards you are working on any time. That's the point. And this is the products that a lot of people don't know. Actually, people were surprised, like, oh, there's so much product actually being developed and being in the market. This is the only product that they have found that companies are using it, and they are open to publishing. So you can see a lot of products, Ruby Tag, Pytag. Even we have LART, anybody familiar with LART? It's a gateway company. They're primarily building on top of Zephyr.
Yeah.
So those were products, complete products going to commercial market. But this was the bots. So for developers, basically there are 400 bots already being supported. Meaning from day one you can just take it, plug and play, and use it. So just as board, you also have sensors already integrated. Meaning if just say you are using a humidity sensor that you are interested in, you don't have to write any code. You just have to tell in this board, this sensor is connected to this particular pin and the driver will load up. This is such a very new topic for embedded system, especially in a microcontroller world. If you are normally working on microcontroller, what you will do is you will go find the source code, you will implement yourself on your build system and all this thing. So I hope you see the difference. And big architecture, like what we say, ARM, Intel, PIMS, EOS, RISC-V, and all this thing. It's all out of box. Architecture layer is well defined. So again, a vibrant ecosystem, development tools, and again, one more thing is there's also this technical steering committee which is open in nature. Again, you can go and open and see what each meeting is going on, how people are planning API, what API is going to get deprecated, what's going to come new before when the code cooks up. So there's a proper governing body behind. And this is my favorite part actually. of showing how Zephyr works. So you can go from bottom layer, hardware platform. So just let's say we take some MCU STM32. We have the SOC. On top of the SOC, you have all the architecture building up. And here where your application lays, it's in the code you are writing to make your product. So you can think of like if you swap your hardware platform, nothing gets impacted on your application layer because those are all fully abstracted. Imagine you are building a product, let's say a Wi-Fi product on ESP32, and then you have the same product for some reason you move to NRF platform. None of the code changes actually on the application side. The Wi-Fi just works out of box, which is also again a new thing for if you have to work with embedded. So APIs are also abstracted in two different ways. There's this low-level API. Low-level API meaning like I2C, you got peripherals, right? So your vendor will normally give you an API, basically a HUD. But on top of it, Zephyr will abstract it their own way or own implementation. So there are certain mapping happens. That's how. So just say the way how you access UART on STM32 will be the same with ESP32. Because you will be accessing using the low-level OS services, the APIs provided by Zephyr. And the mapping happens in this layer. So basically whatever your vendor provides, you map it with Zephyr. You look into the code more details on high level. So and then we talk about connectivity. Connectivity, it can go as low as 802.15.4. They say you want to do a peer-to-peer connection, you don't need a TCP, anything fancy. You can just take and use this. And just say that particular chip has this whatever Ethernet 802.15.4 supports. You just write a driver and map it with Zephyr's API, and you can use Zephyr to manipulate it. Alright, and then all the common networks like IP, what we call it, TCP, UDP, and all this thing. It's already there. On top of it, you have this more complex protocols like MQTT, HTTPS, and all this thing. All this was built on top of Zephyr network stack itself. So this is just a glimpse how network applications are being layered. This is like the driver level, how it's on top with your chipset, and then anything above it is all managed by Zephyr network stack. So this is how it's being layered. So anybody that know about Zephyr. Zephyr started becoming very big after Bluetooth is a big thing because if you look at this chip, Nordic Semiconductor NRF series, the SDK is now by default is Zephyr. So Bluetooth is like how to say any new features coming into Bluetooth quickly can come released to Zephyr, and like today it is 5.3 compliant, and if I'm not mistaken, it is also the stack is kind of compliant also with Bluetooth's 6 standards. Just a quick one. Also, they support multiple modes. Meaning, let's say you have a Bluetooth stack, you want to turn it into a modem. You don't have to write it. Zephyr has a way to turn it into a modem. Like I think we call it HCI transport. So you can use maybe your Linux to control your MCUs and Bluetooth. These are all open standard processes. So okay. Next, stack by default supported by Zephyr. It's already USB 2.0 and USB-C. So if you're working with USB 2 and you need something, they say HDI support, you want to build a key, mouse, I think we saw. So you don't have to go and go find what USB device stack I should use, whether it will work on Zephyr properly. This is already in the ecosystem. You just have to enable it, and if you have the proper driver support, things just work. And this is a huge topic, power management. I don't think if you go into any other courses you get any of this thing. And whenever power management comes, you have to implement yourself. Power management is kind of complex because I just think of it this way. You have a hierarchy of device, you have to switch it off in a very deterministic way. Whatever on the child node and then only just imagine just say you have a sensor connected on U1, say it's a temperature sensor. First you have to turn off the temperature sensor's MOSFET or power or whatever, then only you can switch off the clock of the UART itself. So you need all this proper execution. So that is already PM, power management supported by design and stuff. And it is, how to say, built for once for every platform because we have that instruction. Otherwise, you have to handle all these different things. And device tree. Anybody here knows device tree?
Just about some question power management. Was there any documentation available on how this power is optimized for a particular scenario?
Yeah, there are documentation. So docs.zephyr.org have power management is a subsystem. So if you go to the doc and find for PM subsystem, you will see how power management in a high level works. So did I answer this?
I'll check.
Yeah. Anybody here know what is device tree? Or work with device tree? Basic idea. So I'll just explain in a very high level. So what device tree is, basically it describes your hardware. What is in your hardware basically? Just say you have a board, you can see an example, you have on the board you have I2C1, what are the pins? So here is PV8 and PV9, that means PV8 is the SCL, PV9 is the SPA basically. And then you tell the speed, and then the child node, here you see it's a sensor. So this is a very important concept. So you have I2C and the child node 1 and 2 sensor. It is, and the parent is I2C. This is how the kernel know when it boots up what are the devices it needs to load, what are the drivers it needs to load, and so forth. And there's zero overhead because all these things are compiled on what we call it, built on time during static build. So there's nothing happening dynamic on fly. So this is how you move from one application to one target to another target without having any dependencies. Example, you have your own board file for ESP32. You describe the pin in different name, different format or whatsoever, and then you move to what we call it, to another target. As far as the kernel is concerned, it will just go and check, okay, this is I2C, I need to load up this sensors, and these sensors are connected to this pin. And if anybody worked on any IoT product, you will need OTA support. And for OTA, you have tons of ways. You can do it on your own way, but then there's just tons of work. Zephyr, they choose a project called MCU Boot. It's a very famous secure bootloader, meaning you can do all this encryption and decryption on the fly when the device boots up, and you can use it to do OTA. And there are already some samples that using this backend to stream data from the cloud to update your devices, basically. So that's another thing you can leverage.
Is there any standard protocol or something like that?
MCU boot?
How the OTA will get transferred?
Okay, MCU boot is a separate project itself, a framework to handle boot loading process, and it is as open as you can just integrate it any connectivity you want. It can be HTTP, it can be LoRaWAN, it can be Bluetooth or whatsoever. You get the idea?
ஏதாச்சும் மைக் ஆனில் இருக்கப்போ நீங்கள் டைப் பண்ண எனக்கு கேட்குது. நீங்கள் டைப் பண்ணும்போது மைக்கில் கேட்குது.
அந்த மைக்கு
அவ்வளோ பவராக இருக்கிற சிஸ்டம்
Yeah, all good.
How many we have string?
It will keep increasing bro. Now some 16.
So continuing it, earlier we saw OTA, wait and see boot and all this thing, and then you talk about hardware security things. Just say you need the keys, you need a hash key or whatever. Normally you will go find some library, you will try to implement, you might not understand it and so forth. But with this, in this ecosystem, they already have this thing called TinyCrypt libraries implemented. You can usually use any Zephyr API to handle it. I think since I'm just talking API, it might be a good idea to show a thing maybe. Let's just open the doc.
நீங்கள் பேசுகிறதெல்லாம் கேட்குது ப்ரோ, நீங்கள் மெதுவாக பேசுகிறதா கேட்குது. இங்கே எதுவும் இணைப்பில் இருக்குது.
இல்லை ப்ரோ,
சிஸ்டம் மைக்
அது அந்த மைக் அவ்வளோ பவர்ஃபுல்.
யூடியூப் கமெண்ட்டுக்கு ரெஸ்பாண்ட் பண்ணுறதா? ஒருத்தனே ரெஸ்பாண்ட் பண்ணிக்கிட்டு இருக்கான். ஆல்ரெடி சொல்லியாச்சு. ஆமாம், அதே கொஸ்டின் ஏதாவது திருப்பி ரெஸ்பாண்ட் பண்ணிருக்கான்.
உனக்கு எதை வேணாலும் பண்ணுவாங்கன்னா வேறு பேசுகிறேன் பேச முடியாது. நீ எவ்வளோ ரெஸ்பாண்ட் பண்ண ரெஸ்பாண்ட் பண்ணி
This is the important thing. So you see the crypto API and you get all of the APIs. So this keeps on going, under OS services we got so many tons of things. Earlier what we were talking about, probably debugging. Then under debugging we have so many types of debugging. They say you need a code and it just teach you how to use program and how it looks and all this thing. So I think earlier question was one of it was power management. So let's see here. So this is the style of the doc. First it has all the high level, all the how it works, overview and all this thing. And then you can go in detail. So that explains until the code play. Okay, so far we just covered what are some small things, modules we have and how to cross-reference the doc and I find it. So another big future or whatever we can take, how to say, make use of is POSIX. Anybody here is familiar with POSIX? So POSIX is an API where it uses something like, how to say, like how you build on Linux. On Linux you use, let's say you want to access a UART device, there's something called POSIX API. You can just open, close, have you seen like open, close and all these things? So those are all POSIX derived APIs. POSIX is by default, they have some support on Zephyr basically. Just say you want to do some time, just say you have a time library that is POSIX compliant. It will build perfectly fine on the Linux machine and perfectly fine on Zephyr. Yeah, POSIX is a abstraction standard. In fact, POSIX stands for some, let's see. So yeah, you can see portable operating system interface. Yeah. So that's a big thing. So I have one experience. I was working with an XP on a Linux machine some years ago, and then Zephyr came out. I need to move it here, and I just went in and set up the build system, include the library and things just work. Imagine if Core 6 were not supported, you have to go and map all this thing manually. Okay. This is some benchmark, especially with embedded system guys. Anytime we say, oh, we got something new, people say, what's the speed? Can it really run on the tiny device? Or what can it contact switch? So for that, they have made a report. It's saying like, okay, to create a track, how much time you need. And this is just a benchmark, 120 megahertz Cortex M4. I think most of us will agree this is enough, deterministic enough, and enough. It's not bad. So another subsystem is display subsystem. Just say you are making a watch, you need a nice time display thing. Again, traditional way, you have to go figure out the whole way. Here you can come, oh, okay, the driver, just say there's a display driver already supported for the LCD you are using. Okay, click driver layer second. And then you need, just say, a bigger framework to handle all this thing, the GUI and all this thing. There's something called little GI, like how you have OpenGI and all this thing on your computer. There's something called LPGI, the famous open source graphic library basically, and it's already in the ecosystem. So you can imagine how easily you can, just say your LCD is big, just say your LCD is working on I2C. You just set up a device tree, you just enable little GL, and then you get the thing back, display just comes up. So these are some data structures or services that kernel provide. You have n number of threads are spawn up. You may ask, okay, how the thread talks. So they are all these are the things called as OS services. The OS offers. Just like any other OS, Zephyr offer all these things: P4, I4, stack, message queue, mailbox, pipe. And so that you don't have to implement all this thing on your own. This works. Okay. So this tracing and debugging. So this is, I think, an open source. No, this is not open source. This is called a Sega system view. If anybody of you used it to do tracing, you can see all your thread info, how thread is happening, and all this thing, all the info. Basically, to do most probably to do performance analysis, how its thread is working, and any of your board, like we mentioned, we saw the 400 boards, should have this thing works out of box. That's the beauty of it. And we are not limited to this. There's also called CTF. Basically, there's an open source one. Just say you don't, you just want to print it on the console. Just say you just want to see the stack. Also, so such options. I think this is a bigger plan. I think now it's 3.3, 3.4 release plan. What are the big things going to come up? So this is a quick, how to say, a quick view of how things are moving on the open source community side. You have contributors pushing to development, and then development will just keep having releases coming out. And release plans are already planned, like okay, 3.2, and then 3.3 will come after 6 months or so forth. That is already on the documentation, which you can take a look. But the whole point is, after certain releases have happened, there are also some LTS support version. Zephyr is committing for some X number of years. So you can, just say your product is out of market, you don't have to worry that, okay, some new vulnerabilities detected, I need to go move to a newer version totally, because there will be backporting, testing and all going on by the community itself. And it's totally auditable, and at some point I think now they have this security auditable thing, so they have a certificate release also. This is a separate repository, so that they keep it clean for secure purpose. So what are the things checked in LTS support? Product focus. So product focus meaning they are expecting customers already hit to the market. Product is on the field. So those are the things regularly backported. Let's say your driver level have some bugs. Someone figure out that will be backported to any LTS version. although we are already on 3.1, 3.4 or some newer versions. Okay. So you can imagine 1.14 is like very old version, which the code of 1.14 and now will be totally big change, but things are still being backported and some changes are coming in. So this is another thing, SBOM. Basically, any company that using open source product will want to see a BOM, a bill of material. What are the open source licenses you are using or whatsoever on your source code? Because if you notice all your source code on the top page of it, it will have what type of license you are using, Apache 2, GPL and all that. Zephyr itself by design it is fully open source, Apache 2.0. But you have all these modules that you integrated. It might not be GPL, it might be GPL or some other things. So you can just run this thing and it will tell, okay, these are the relationship and these are the licenses, how they interact and all this. This is the body that they are using to handle CVEs and all this thing for security purpose. And this is some project by the Linux Foundation. It's voluntarily you can join that parties and all this thing. Just a quick thing, the ecosystem, about the ecosystem, who's saying and how things are being handled. These are all the gold, platinum members. So basically they did sponsor Zephyr for all this thing. And you can see some big names here, Google, Nanda, Nordic and all this thing. So you know that they are seriously contributing to the project and they are utilizing it. And these are some silver members and again the community. And these are some tools basically, like for today we have a hands-on session, we will be fully utilizing VS Code, but then the community have extended to Eclipse, CN, and platform editor and all this. And then of course debuggers, Sega already by default supports Zephyr. If you give the argument Zephyr, the tracing start working. That was not the case when just 2 years ago or something. That's the thing. And then you also have a simulation partner. Renode is working on a very good CI/CD platform to do all kind of simulation. But it does things like, okay, it builds, it tests on your ESP32 and your another target, just say it's Nordic or whatsoever, on a real hardware and do all the testing. Basically, it's a framework to do this. And do all the so many people coming into the picture. And again, you have so many companies providing training, consulting, and all this. And in the big picture, you have all these security libraries, and then if you're doing something like machine learning, you don't have to go and take the pesky work of integrating TensorFlow right or whatsoever. You just get out of the box. Somebody has contributed to. And here's some numbers how contribution is doing compared to others ever. Surprisingly, since 2023, it is a big. 2022, it's a big hit, and during the COVID, actually the contribution went really, really high. And Meetup currently it's like one of the most famous RTOS, and people are getting more interest. And then this is some stats of the commits on the GitHub. comparing with other thing, and Zephyr will be it's on the top. So that's from I just done a basic overview of what Zephyr is, how the ecosystem works, all this thing. Any specific question or answer? Any audience group?
Not at here. They're all good.
So you want to do a quick
In labs, yeah.
just hide.
Yeah, I'll do.
So
You just give an intro about labs,
so
then I'll.
next, what we are planning for the next agenda is basically I'm here Siddharan. So what Siddharan works on doing education at that basically. So we work together to build a lab basically to make Zephyr entirely run out of cloud. You do the entire development out of cloud and you can deploy on cloud and test. And today our hands-on session will be happening in that way. And it's not only about Zephyr, but we also get other IoT connectivity and all these things so that we can use it. So Siddharan will be introducing to you how this thing works. Okay.
Bro, give on your set. Bro, you need to check the stream. Just switch the scenes, bro.
I don't need to write scenes.
Basically, you don't need to. Hi, so I want to tell you about this cloud development. So far, whenever we are doing IoT hardware, so it's all like things can never happen over cloud unless it is CI/CD. So there are a lot of limitations with that. Not just that, it is very with respect to any sort of online development. Like, let's say you want to do something in IoT, you have to do tons of things yourself. You have to have your own servers, you have to have your own infra. So, in here, so basically I want to tell you what we are doing here.
So,
I present to you
private network.
Self-made Ninja Labs. So Self-made Ninja Labs is like a platform with where you can access any type of cloud development, not just development. You can connect it to any type of backend services. So it is like a mini AWS. AWS is something vast. I maybe you can tell like I'm hitting some 1% of what they are doing, but still it is the essential 1%. So in labs we have
you're on private network, that's why you just close this thing, and I should have one locked in.
Yeah. So in labs we have created a lot of laboratories. These are just some simple ones, but we are contributing in the areas of cybersecurity, Internet of Things, software development, and hardware development. So all these things are computer science. So we cannot like take one thing away from this and things doesn't make sense. So we are creating laboratories for multiple purposes, and you could see I have like multiple labs here. So one is called Essentials Lab. Sorry, zoom in. Yeah. So one is Essentials Lab. We have Node-RED Lab. We have RTOS Lab. So these things make development basically very easy. And we are going to have a live hands-on session and with the help of all the tools here. So what we have created is we have created server instances for different use cases. Let's say Zephyr is a use case. Node-RED is a different use case. So Essentials is where you code. It supports over 50 programming languages. So you can code whatever you want, and these acts as a real life server. So I have a personal website of my own, and this entire website is hosted in labs only. So just like how we host things on AWS, you can host n number of websites in labs, and we are providing a way for people to add domains, and they can connect it to any labs, and then they can use anything on internet. Like you can code on internet, you can host on internet, you can have all your services on internet. So when I mean services, I literally mean it, because we have managed all the services that is required to do any complex application. So let's say you need a MongoDB server for your application, IoT application, or some software development. So it is all here. So how I see IoT versus software is they are basically the same thing. Just the software is running on a different place. So if there is software, then there should be some data, and if there should be some data, then we got to process it. And processing won't happen right on the client device alone. We have to send it to the cloud, and then that is when it is Internet of Things, right? So let it be a software, let it be a hardware, whatever it needs cloud. And with labs, we are giving an amazing cloud infrastructure with which you can do whatever you want. So we are giving all popular backend technologies. Even this RabbitMQ we have managed, and RabbitMQ has a lot of protocols. Like RabbitMQ has AMQP, RabbitMQ supports MQTT, and MQTT is one of the very popular platform that we might need in IoT. We have a lot of other protocols, right? So RabbitMQ platform gives ability to convert messages between multiple protocols. So if I'm sending a message in AMQP protocol, that can be forwarded to MQTT if required. So we are giving all such services that enables quick development. You don't have to worry about hosting these services, managing these services. Just go create a username, get into your lab, and you can start coding. So with respect to labs, so I want to show you how labs work. So we have Zephyr lab here, and so all these are like managed containers. So these are all containers where you can code, and to access labs, you can do it in different levels. The basic level you do this, you can code on web. You don't need anything else. Like you don't need to run a VS Code. You don't need to install anything. All you have to do is you have to first deploy the lab, and then hit code, and it basically opens an IDE. Yeah. So like this. So your VS Code comes to the browser, and you can do all sort of development just from the browser itself. So once you launch the code server, you might need to get a password, and so yeah, the VS Code is here, and this just runs on web, internet. You don't need anything else, and you can access your terminal. And this lab is completely pre-configured to work with Zephyr. So you don't need to install any tool chains. You don't need to configure anything. So the entire build process can be offloaded to this laboratory. And I want Manoj to show you more about what you can do inside this lab. So it is basically, we have multiple scenarios, and there is a lab for every scenario. So we even have a Node-RED lab. So Node-RED is like one visual programming tool with which we can easily do a lot of things visually. So I want to show you how our Node-RED lab works. So our Node-RED lab also works public. So we have this public URL that we got to copy and paste, and you get a very secured one, because when we designed all this, we kept security in mind. We are like cyber security. We know how security is. So when we designed it, we kept security into the design, so that everything that is accessible from the labs, like even this Node-RED server, as an RTOS server, all the other MQTT servers, MySQL, MongoDB, anything that you name, everything is like very secure. And if you see AWS has like basically one service alternate for every open source thing. and I don't want to do that. I want to take open source and manage them because that is what people will use. I don't want to reinvent the wheel. Open source are all already safe and secure, and so we don't want to as I said, reinvent the wheel, and that's why the lab. So we are bringing all these services, and with the help of Node, you can easily visually code even code things like. So Manoj will be explaining more on this example so that he has created.
So we have one actually. So
you can take it from here.
so we are just one very done.
Okay, sure.
So basically this thing is streaming, this 9 what you're seeing here is streaming right here. And it's connected to Wi-Fi, and you can on and off hours so we are just demonstrating bi-directional flow. But the whole point is just say we had a big audience today here, and we have to do hands-on session. We can't expect people to install Zephyr RTOS on every people's machine. And to make this kind of thing happen, although it looks very simple, you need web server, you need MQTT server, you need configuration, you just have tons of things. Although it's open source, it's gonna just get missed. You need to download 10 GB, 20 GB of stuff, install, and the machine might not work properly. So this thing is entirely containerized, so things are all on the cloud. So, and the whole point is, you can just put your first step very easy, without any issues. Most of the time what we see is when you come into the picture, they just get scared because by the time they just come into the world of installation, especially in the Linux world, they just fail. So we just thought, okay, it's all pretty cool, we know each other, and we're doing something similar. We just brought Zephyr into this picture. So each one of you will get a login access later. Immediately you can open any projects. In fact, we provide a sample project. You can make modification and immediately see things just working. And node rate was one good thing because visually you can do a lot of this is just very simple one. Things like this, you can just get things very fast.
So, as we are talking about labs and we showed you code server that is running on web, we want to take the experience a bit further, and we have put a VPN layer here. So this VPN layer lets me connect to everybody who's on the network. So we are running an academy, and I basically want my students to be connected all the time. Connected in sense not through social media or Instagram. What I'm telling is literal network connection between the systems. So let's say I want to get into my friend's computer or my student's computer and see what he's doing, and he's in Australia. I don't do TeamViewer or things. I can directly SSH into his machine. And people might consider that it's not secure because of all the things that is on the surface layer of the internet. If we do this in the surface layer of the internet, then things are going to be trapped anytime soon. Like people might hack it, people might DOS it, like denial of service will happen. So we cannot be sure, we cannot keep all sensitive things on the surface layer of the internet. So we have this VPN. And if you want to access all these services that we have showed here, like the MySQL, MongoDB and things, you have to connect to the VPN. So that you can get into the service, you can even port forward them with the help of VS Code, and the services are immediately available in your computer. So it's just one click. So you just go to these services, and I hope you all have used VS Code, and VS Code has a section called ports. So near the terminal you could see there is a section called ports. All you have to do is copy the string, paste it there, and immediately this service is available in your computer without zero installation. And you can access the port is available for you. So with the help of all these things, we are going to show one example with the help of RabbitMQ, and we are going to see this MQTT thing like how it turns out. So that is the same example Manoj already demonstrated, so that there is this two-way thing. And I want to show you some of the things that you can do from this server. Let's say we take RabbitMQ as an example. I cannot allow MongoDB on the surface layer of the internet, but I can allow RabbitMQ because RabbitMQ is just a message queuing service. So if I keep RabbitMQ inside the VPN, then that makes no sense, right? If I make RabbitMQ inside the VPN, then that makes no sense. So what I'm doing is, we are just ensuring that people will be able to connect all the IoT devices, any device that they want, any device that they want to connect, that they want to access, wherever that may be in the world. The logic runs inside the VPN. The logic runs inside the VPN, but it can connect to the devices that is like from anywhere in the world, because the connection happens on the internet, but the logic is running behind the VPN. So if you want to get into the logic, get into the system and change the logic, that is where the VPN is securing it. So you can't do everything in the code server. Code server is very limited. What I mean by code server is what we ran here. So this is basically code server. I can do Linux commands, I can do whatever I want, and the best of best thing is with the help of this I can work from anywhere in the world. There is no connectivity issue. If I want to build some big Docker build, I might need some big internet. Without that, one big Docker image takes tons of time. But with the help of this system, we can even build Docker images very fast, even with 1 Mbps. So because always the internet speed inside this system is like very good. So let's get into this essentials lab, and I'll show you more. Oh no, not this. Let me go to the stage. So we are not only working on these things. Just the lab to practice. We are also creating laboratories which people can practice on their cybersecurity areas. So you could see we have created a lot of laboratories here. So these are all like challenges where anyone can get into this, understand what the mission is about. So these are all like missions. You just have to read the mission. Then there will be some vulnerable code. You solve the code and you get some score. And that takes you forward in the league. So it is like playing some game, but with the help of your programming knowledge. So that is how it basically goes. So this platform is completely created for learning purposes, as well as you can do, because we believe learning and doing always should go hand in hand. So if we don't learn while we do, or if we don't do while we learn, things doesn't work out. So we created this platform in a mind that one should get an experience on everything. Let's say we are talking about Internet of Things. We are not talking about embedded. We are not talking about just one software or something. So we are combining it all together. So all these things matters. So however we design the systems, if there is one small security loophole in the way we communicate our MQTT, then boom, anybody can take over my device. Because this communication that is happening here, the two-way communication with which I can control the lights or something, this is what we call as smart appliances or automation or whatever smart devices that we do. This is what it means, and the way how the communication is established, and the way how all things talk to each other, how the data is processed, how let's say an ML is getting its data. So all these things has to be in a perfectly secured way, and utilizing this platform even teaches a beginner to bring all these security practices into their real life. So let's get into I want to show you one node that we have here. So I want to open my Node-RED and I want to show you something that I've built. So this Node-RED that we are showing, people usually run it on their devices, like in Barwood, people run it on Raspberry, and they use that to control a lot of things. People run it on their computers and it helps automate. But when we take the same server online, then security is an essential thing, because I can't like leave my Node-RED running on a server and if anybody accesses it, then that is a problem. So the Node-RED that we are configuring here is always secured with the password. So this is one simple flow that I have created with Node-RED, and the flow helps me understand all the containers that are running in labs, because in labs that whatever that we are doing here, thousands of containers are running, not one or two or three. In labs, thousands of containers are running, and since we have thousands of containers, we have to know if somebody abuses it at any time. And I don't want to write scripts or admin panels because I don't have time. I can focus, my time in, different areas where I can be productive. But I still want a dashboard where I want to see if somebody is abusing, and I want to know without logging into my terminal and getting, see the logs and or checking the usage. So it is not quite good, right? So Node-RED helped me. I just created this overnight, and Node-RED helped me build a dashboard very quick, pick the data from my devices and plot it in a map in a real time. And also I've added Telegram here, a Telegram notification service. And if somebody is abusing a CPU, I instantly get a Telegram message. Like if somebody is trying to attack somebody or some attack is incoming, both ways, CPUs will be abused. Yes? So I'm monitoring the CPUs, and I'm basically taking data from an API, and so I could show you how the UI works. So whatever I've created here, mapped here, you could see in a beautiful UI. So and this UI is real time. So if anybody is like utilizing something, see I'm seeing one somebody is using like the full CPU, and it gives me a visual idea of what is happening inside the laboratory. So inside, when we are giving it to other customers, when we are giving it to other institutions, people at times don't know what they are doing and they mess things up. So this is added as a security feature, and what I'm telling is this is live. Even if you hit this URL, you'll be able to see the same. So it helps us admins to create a personal dashboard for ourselves with which we can monitor things. So if I'm having few devices that is here and there, I can connect it all together, create a dashboard instead of coding things in live. So before I get to code something in a very standard way and moving into production, that is a very long process. I just want to see it working because nobody else other than me is going to use it, and Node-RED is a beautiful way to do that. And today we are going to show you some demos with the help of Node-RED, and this will give you a complete idea of how IoT can be simulated with Node-RED before we can push it to production. And Manoj is going to do a lot of things inside Zephyr, so everything is going to be hands-on. And so far you have any doubts regarding labs or its infrastructure, how maybe its security? So if you have any doubts, you could throw in. So
I have a doubt on that. So is that ESP connected is public? Is that ESP public?
Wi-Fi, it's connected to this.
Yeah, this ESP demo, right? That you showed. Yeah, the ESP is connected to the Wi-Fi now.
So it is not only the LAN or it is public?
Yeah. Even if you connect it to some power bank, it will work.
So the connection to the laptop is just for powering the.
This LAN, huh?
When you are connected.
Yeah, that's just for power.
Okay.
We just have it for power.
Okay.
So the connection is wireless. Even if you connect it to your laptop, it just takes power from there. But we have connected it to the Wi-Fi here.
Yeah, but will it turn connect to the internet and?
Yes, exactly. You can, even if you are doing it from Australia, it still works. Yeah. Maybe I can share you the URL. You do it, flip from phone, and you can see.
Okay, so this thing is, it has a particular IP assigned to it.
We have. It's not like it has a particular IP assigned to it. It is connected to Wi-Fi. It has internet, and it is connected to MQTT on SNA Labs.
Oh.
So now this MQTT is continuously being streamed, and because of that, if you change something, maybe I want to show you this. So I'm flipping it now. You could see, right? This connection is made through MQTT. Yeah. So messages are continuously being streamed. And in today's demo, we are going to give you one of such device, and you are going to see it hands-on, like how things will happen, and you are going to create your own MQTT servers in our laboratory. I hope you all have already received the temporary username and password for the same. So you could experiment the same thing and much more. We are also going to provide you some RGB LEDs with which you can practice, and Manoj is going to demonstrate how you can do the same. Because LED is basically a device, right? And if you want to add a device to an operating system, then you need a driver. Without a driver, you can't do it. So RGB is such a thing that requires driving. If not, you cannot get absolute colors out of it. And so we are going to do this RGB example completely from scratch, and we are going to use SNA Labs and do the same experiment that Manoj has already set up, so that you could get a complete working idea of what we are trying to do. So because Zephyr is a very complicated thing, unless we get a hands-on to it, and unless we understand it in a deep way, it never makes sense. So we are going to bridge that gap here. So that is the whole point of arranging this, and so we will go on with that. So take up. Yeah. So if you have any doubts with the experiment, you could always ask us. We are here to help. Okay, so the first half of the event, we plan to give high-level picture how Zephyr and how labs going to be used. I hope you get some idea how labs going to be used. And now I'm just picking some topics that are important to set context before we start diving into the code and all this thing. So this is a very good diagram. So on the top here you see board. Am I right? And then you see all these SOCs. So this is how entire things actually drill down in Zephyr. So just say you say you are using a board called SCM32, some board. So the first layer Zephyr knows is it knows about your board. It derives to bottom. Okay, what SOC it is using, what SOC is present on the board. And then it loads all these things, all the information. And then it goes until the layer where what SOC family it is, then it knows what UART peripherals, all this availability in the SOCs. Clear? And then you see the CPU layer, and then you see architecture layer. So the beauty you get out of this drill down effect is this architecture code basically just say STM32 runs on ARM Cortex. Bro, mic வெளிய வைங்க. Bro, wait, I'll adjust it for you. Come here.
So the beauty of it, just say you're using some STM32 board and the board has ARM Cortex M4. The M4 code is basically using Zephyr's architecture code by ARM M4. It is totally same code as what you will get in another SoCs, ARM Cortex M4 or whatever, inside a non-big semiconductor. Because those are common codes. So that's how things, when things are architected properly on a high level, you can reuse lots of code. Whatever bug you get on M4 on this processor, you'll see it on another platform as well. Because the same type of code is being done, and it is able to do because the project is orchestrated by that. So you only inject code that you need. So just say in this case you have STM32 board, you have STM related SoC. So yeah, you inject that particular code and then that particular driver. Otherwise things are all whatever can be shared, it's shared. Clear? So this is one example. So you have STM32H7. Those SoC is this SoC, and then the series is H7, and then the family, and then the CPU and the architecture. And all this thing turns out to mean something on the
Instagram
code.
story
How? Just say you have this H7. H7, all family of H7 will be using the same driver. So the moment you configure H7, the same vendor HAL library is pulled and being used for all S7 family, instead of you simply importing codes and all this thing. So your project just lays to just contain application code rather than all these things. That will just pack all this. Cool. So I guess now we just jump into seeing some code example so that that you get a picture. So I'm just randomly gonna arbitrarily open a board and show some sample. So now we are in the kernel code basically. Basically this tree what you are seeing here is in the kernel, and I am opening the folder called boards because that's what we saw right on the top layer. Board is the first part, Zephyr C's. So in this case, okay, I'm gonna go into some ARM related board, and I'll just pick one of my favorite board. Just say I'll pick Nucleo. Just say I pick Nucleo. Oh, in fact, this is a board contributed by me. So I pick a board. So this is called, if you notice here, Nucleo underscore H7A3 ZI DTS. DTS stands for device release source. And this file basically, let me zoom a little bit. This entire file is just there to explain your device, basically, your board. So let's see what are the things we have explained here. We are saying, okay, Zephyr console by default runs on UI3. And you have all the child nodes. These are the LEDs. So if you look at any development boards, you have some LEDs on it, right? So this is how it's being described. Okay, green LED, and then the child node has this GPIO property, and which pin is that? If you notice STM32 ecosystem, you have port and pin. The way how they do it is GPIO B stands for port B and pin 0. And it is an active high smart configuration. This is a thing. And you just describe the board, okay, what are the things available in the board. You can even go until the level, you describe the clock. the crystal on the board, right? Because the clock is not in the SOC, in the board. So just say tomorrow you are going from 8 megahertz to 16 megahertz. Those days you have to go into the source code, find the thing and just modify it. But today with this kind of abstraction, just go modify here instead of 8 megahertz, you change it to 16 megahertz and recompile the code. Pretty good. This PLL configuration and all these things. So one last thing to look at is we saw UART. So just now we saw default Zephyr will use console on UART3. So this is how UART3 is being configured. Current speed is 11500. All this data is fully centralized. Just say you have 3 sensors. For UART it doesn't make sense, but for I2C, let's say 3 sensors are being using I2C. Those days you have to go manually for each sensor. You need to tell which I2C, which speed, and all this thing. With this, you just have a common thing. You have a common API to extract all this data and source code. So that's device 3. Then on top of device 3, you will ask how Zephyr will know what are the SOCs being used. That is inside basically one of the K config. K config is the way how you define config basically. This is my something called on the same directory, on the bot directory nucleo. I have something called config SOC series STM3287. Yes. Then Zephyr now if I compile a code for this bot, the bot has this H7 series SOC. And what exactly which SOC exactly is also check yes. And then you have all those other tons of things. This thing pretty clear. So let me just go copy this thing so that you get some context. I copy this thing. Paste it. So this is from bot layer. We jumped. So in bot layer we saw that this thing is set up SOC series STM3287X. So what STM3287X contains? It has an ARM processor. It has it used STM32 cube library and all these things being selected. So you can get the picture how things are being derived eventually. And from here, if you notice, these things are being cross-referenced in source code also in your driver code or something. Just say you need to do some special initialization in your driver code. This is SOC config driver code, basically SOC layer. If you're using H7X, you see the code how they are handling. All this thing comes into your code. Eventually, you can access all this. We call this config parameters being accessed in your code as well. From your device tree and then your K config, all this thing makes sense in. Okay, this is one thing. And I think another topic that I would like to show that is this. You got a YAML file here. Any board you go, you have a YAML file basically. What this YAML file does is, you see this thing called support.arduino, GPIO, UART, all this thing. That means every time somebody is pushing a commit to the project, this bots will go through all this test by its own by Zephyr CL. So whatever bot is there, you can pretty much say that okay, things will just work. All GPIO, UART and all this. This is how the runner knows what are the tests I should done on this bot. What are the peripherals supported by this bot, and I should explicitly do the test. And the test codes are available something like this. So this is ADC source code. So basically, based on the device, all this thing, it will pick which bot it is doing, and it will run some logic. Some, they might inject some faults and see whether the bot can detect all this thing. All this thing you get as a framework. If you do it in bare metal or whatever, all this thing you have to figure out. And I think most of the people won't even put effort to come until this one because it's already gets so big. That's why you can leverage. So let's take a live demo. So to do anything with Zephyr, basically you have a command line tool to do it. So Zephyr has a tool called West. West is like the front end handler of the entire whatever Zephyr can do. For example, I put West bots. What it will do is it will list the supported bots. So So I get all the list of bots I'm getting. And now I'm just going to compile a very simple Hello World project. So let's see how the Hello World project will look like. So very simple code, just print K hello world. Simple, right? So let's just see how to build this project. You will be very curious, okay, how we going to do a build. So to do anything with Zephyr, you need to use the West tool. It's like a helper tool. So I'm just going to put West build, and then dash hyphen B stands for what bot I'm going to use. So now I'll just say I want to pick about Nucleo X723ZG, and then what project I want to build. So this project was inside sample hello world. So I'm just going to provide sample hello world, and hyphen P is for christening, meaning it will always clean the repo before it builds. And I just click enter. Zephyr will automatically go pull whatever toolchain is required for this particular bot. Which GCC I need to pick up, which RTOS I need to go find from the bot view I showed you. That's how it will define its way. And now it has built that firmware. It is showing okay how much memory is being used on flash, RAM, and all this. You got the binary already. At this point, you can take it and flash it. So now I'm going to show the beauty of it. Instead of doing the same project, instead of using Nucleo, just say I want to build it for ESP32. So just build. ESP32 runs on totally different toolchain, extends our toolchain, and Nucleo runs on ARM. But you see, just out of box, it just built it. The expected outcome is the same when you put on the target. So far, clear? best way, now I'm just going to show some samples. Let's just here. So what I'm showing here is just the folders that exist on the kernel file, but the important file to get started or what you want to do is something called samples. So you go into samples, you have tons of samples basically. So we talked about POSIX earlier, we have POSIX sample, and then you want to write some driver, you have driver samples and all this things. You get the point? Okay. So just say, okay, let's do some while test now. We have a sensor. We just pick a sensor, just say some sensor, what do we use? Something crazy. CD 280. And we just best build here, just say about we just provide the board. Something. So I just randomly built this BME 280 project. Basically what it means is if you connected the sensor, how this sensor wants it, you can basically read the value of the sensor or so forth. So you can see how sample is built inside the kernel itself. You can easily get started and all this thing. So maybe we can take a look at how this works. For example, so this is how the BME80 is being referenced basically. There's this BME80 compatible is how you pull the how to say which driver to pull in, and then the pins and the register stands for the address of the I2C. And you can see you can move board to board and get the BME20 just works out about just by doing some command line access. Anything we should cover?
No,
any questions before we take the first half? So basically we have just shown how moving from different platforms is so easy, where you can find the files, how it is being cross-referenced.
If you want to introduce a new code which is not listed there, or let's say a family of code which is not listed, what are the minimum things required to start coding?
Okay, so that's a good question. So the first thing on my what I will do typically, I'll just tell what I do then. So what I had earlier, the link I had. Let me go back here. So there's already a guide, board coding guide, but what I want to do is, so first thing I will know, okay, my board is not there. Then second thing I will check whether my SOC at least is there. Because there might be, you're building a board just for your product, your company's product. So there are cases where that is easy then you just have to define board related file. So what is needed in the board file bare minimum is So you can see the point here, your board directory should look like this, bare minimum. So it contains all the configuration file which associated tool and all this. So this is the bare minimum. So if you are looking at some scenarios, let's say you have some new architectures or new SOCs that are not being introduced, then you have to go into SOC layers and start working. But just say if on a good time that okay, most cases we are using like STM32, just say most of the SOCs are already being contributed and managed by the vendor, then you will just be handling this layer. And what that layer does is all this, you fill up these files and it just works out of box. When you do West bots, your bot will start appearing.
So one manufacturer may not support all of their boards to be compatible with Zephyr. So if, so let's say STM has 100 MCUs and they support right now is 50. So for another 50, let's say they have different code on ARM. So how will it get into it?
Oh, okay, good question also. So that's why STM has this thing called SOC family. The complicated part will be from the family bottom down. So most of the things will be figured out already. Just say you are using a STM32H7 family. H7 family will be already being configured. On top of that, H723 AG, the version you are using might not be there. So the SOC file only you will be defining.
Okay, I was referring to the.
Oh, so you mean like even the family is not there. Then you have to introduce file on the SOC layer. But it is so systematic that you at least you know where you can go and find things and what you needed just by looking there.
So is it also documented?
Yeah, I won't say fully documented, but from what I'm telling is okay. So SOC layer. So what is SOC layer basically? So how it will look is okay. Let's go to SOC layer now. Instead of board layer, we have to go to SOC layer, then ARM in this case, then under ARM, what do we have? So we have all kind of, if let's say for sake of demo, we take STM32. Under STM32, it's already being, how to say, differentiated by family. And by family, you need to introduce all these things, some linker file, some SOC initialization if you need some special initialization. Then you can see from one vendor to another vendor, these all follow similar standards. So here you see they have contributed for X4, X6 and all this thing. You just have to add, if your thing is not there, you just have to add it. But if your family is there already, then fine. It's a good example. Recently, I am working on FPGA basically. So it might be a good idea to look at my how I am handling it. I'm planning to open source this as well. So this SOC is not being supported at the moment. So it's a complete BSP, board support package. What are the files? And my commits are pretty clean. So let's just look at it. Let's just okay. Board. So I'm just introducing commit SOC this file add initial support for this SOC. And under this SOC, what are the files I'm introducing? I'm introducing some CMake file for the build system to know how to do it. And then I'm introducing the kconfig series file for SOC. All this thing. So now the next person that want to use this chipset on their board don't have to do all this code input. Because I have handled the SOC layer for that. This is SOC layer. Then just say board layer. I have separated my comment in such a way, so it's really good. So on board layer, I'm introducing all this particular code just related to board. Because the project is so systematic that I can even do my commit such a way. I go layer by layer. That's how I tested this project. Did I answer? And then this is a totally new platform, so I'm also adding drivers. So this SOC doesn't have a driver, a GPIO driver. So I'm just telling to the build system, hey, when somebody says the SOC have this using this config file GPIO Phoenix, start loading up this particular driver file, and this is how you should go and find. And then the high level API will start taking form. Did I answer the question? I think this is good example.
Yeah.
Anything, bro? You have any question you personally want to ask?
Yeah. I'll go with it. So, let's say you want to. Oh, I have to. So let's say if you want to add a device, you're doing it for FPGAs, right? So this code that you're showing is already the support that you added for FPGAs, yes. So if let's say, I'm extending his previous question of adding one SoC family itself. Let's say I'm making some new architecture. So SoC families are basically architectures, right?
Okay, just before we go in depth in the question. SoC family doesn't mean architecture, but it will be using some form of architecture. It can be RISC-V, it can be something.
Okay, so for that the CPU should be existent. So what is the difference between the architecture and the SoC family?
Architecture family means it's architecture level code.
You mean the CPU architecture, the code x86?
Yeah.
Okay.
Okay, so maybe we can show. Now we see what's that architecture level code. So you just go into architecture. You have RISC-V. Under RISC-V, you have to do so many things, right? Like how you should handle the interrupt, how you should handle factor error. These are all common for all architecture. So those how things are abstracted.
Okay. So you go up and now go back to the family SoC thing. I mean the SoC layer.
Okay.
In code, yeah.
SoC, okay. So we had one open here ARM, and then we had the open Nucleo here. So yeah, we have the C0 open, some SoC.c code, yeah. What's the question?
Okay. Go to the top directory, please. Can you please go to the SoC directory?
Yeah, we are in SoC now.
Okay.
It is broken down by what architecture basically.
Okay. So all the architecture's code are kept in the same layer. So depending on the architecture that you run, all the methods will automatically propagate, right?
Yeah.
So let's say there is one functionality that is not available for ARM, and maybe such things available for RISC-V. Maybe it depends on the architecture level thing. So will you be able to match it up here, like port it here? Is it how the SoC works? Because the tree, maybe you're adding support for more things, but something doesn't support at the SoC level. Maybe something that doesn't support at the architecture level. Will you be able to match it out at the SoC layer?
So answering to your question, just say you are using one of the ARM board. Just say you introduce a ARM family itself, and it is a ARM. Just say it's ARM4 ARM or whatever ARM it is. The source code you see here will able to use all the ARM features. So
okay, only it can use the ARM.
Yeah.
Okay.
That's the whole point of the abstraction.
Okay, so
and why we have this SoC layer is basically this. It's extending from this question. For cases you have ARM and for NXP, and then you have ARM M4 for STM32. But on SoC layer, sometimes initialization level will be different. Like how you do initialization, the order of initialization and all these things cannot be abstracted until the architecture level. Because they have taken the architecture and put two things together, their own bus and all these things. So those things happen in SoC layer. Normally SoC layer will tell, okay, when the core is up, you should do, maybe you need to go turn on this.
Okay. Okay.
Yeah. Now that you talked about that, I think since we have some time, I'm getting a very good. I saw a very good presentation on the boot initialization boot of how Zephyr boots up.
Yeah, that's a very good thing.
Yeah,
We
so
need
I'm
that.
going to show that, which will explain or give more mental model basically. So this was a video, but inside the video had a very good. So this is high level what Zephyr does. Every target when they first power on, they go into something called a reset vector. That's how they know, okay, it's like x0000, and then they have to set up stacks. That's how then only C code can run. So most of your code in architecture layer will be most likely assembly, because you don't even have a C stack yet. So you get all this early code preparation. Then when you have the C stack, then only the power of Zephyr start coming into picture, because Zephyr is 90% written in C. Then only you get the kernel initialization, kernel some stuff comes up. Then only your scheduler comes up. Then only scheduler will pick up your main first threader to run as a thread. And then only your threading services come to play. So if you are writing driver level stuff, you need to understand how things works, because you don't want to go put thread stuff in your driver basically, because basically that means there will be a dependency issues and so forth.
Yeah.
And in detail, if you want to see how in detail all these things will happen, so you see how we have done all this abstraction, which architecture, based on architecture they are doing some, calling some APIs and all this. And all these APIs are being called based on some configuration, how it eventually run into a main thread. And there's something called run level, like how you have in Linux, run level. Same thing applies to Zephyr. For example, you need to turn on your network driver up and initialize it before even your network stack comes up. Then only a network stack can listen to that driver. So you need to handle all those things. Zephyr by design is providing this, how to say, the flow, good flow. And you have a priority basically. Just say you have, for example, most very priority thing in Zephyr is you need to get your UART before getting other peripheral up, because then only your console will be up. When your console is up only, when you see errors, you can see on your console. So those things are being handled by this run level. So it will take the device, whatever device you have put on the device tree, it will see based on the priority, it will load that up and load and initialize it. Pretty clear?
Yeah, that answers it. Nice. So the UART is initialized by the boot process itself.
Yes.
Boot itself will do that.
So
Okay.
if you go to the device tree, if you notice on the device tree,
Yeah.
just say we got something called. You see on everything you got something called status okay. What that status okay means is it's telling the kernel that this device is going to be consumed by the kernel. If you say status disabled, meaning the kernel won't even run, initialize this device on boot up. So you can see if you are doing normal coding like how you will be doing bare metal like 5 years, 10 years ago, all these things fully manual. It's a pesky tedious work. I forgot when the last time I initialized a driver basically, because things are being cared for. And so far, and then again another big thing is, we all have a habit of writing code, not basically if you write code in C, we like to repeat things. But here not the case. So just say I have UART 3 now, I want to add UART 4. I just copy this entire block code UR4 and just change the pin. The same driver will just initiate an object. So there's a concept of instance in every layer of Zephyr, in driver and all these things. So if you already support your driver support instance layer, you don't have to repeat and repeat. Like in bare metal, I see people like repeat and repeat and repeat, right? They just take and copy paste. So this is one problem which is solved very nice. So just if you are curious, basically what it does is it's just keeping a list of all devices, and when the system comes up, it just runs in a for loop. And based on it's already been sorted already in static build time by some Python script where the objects are. It just takes it and initializes it.
So can this device tree be extended for other users? Like can this be extended, let's say I want to add more devices on top of the same chipset. So how this device tree can be extended so that if, let's say I'm taking the same SoC and I'm customizing my own board on top of it.
Okay. So your question is you want to add devices like peripherals on the SoC itself or on the board?
On the SoC itself.
So SoC itself, maybe the SoC have UART and you want to add a UART.
Exactly.
So there's two levels of device tree. We have device tree on the board level. So board level explains things on the board, what is on the board. So in your case, you have to go to the device tree on the SoC layer. So if you want to see an example, let's take it.
So every layer has a
SoC
device tree.
and SoC and the board file. So let's take a look at H7 STM32. I hope everyone knows STM32 H7 SoC. This SoC is describing device tree file. What are the things available in the SoC inside? So first layer, what you have one CPU. What CPU is that? Cortex M7. What the CPU has in its heart, it has a child MPU, memory protection unit. And at what address it is being available? You see this address and this. And it also says the address size. So if you are doing something wrong, just say it checks basically address spacing basically. So if your address are colliding or whatever, it will tell on build time something is screw up. Before even your driver go and touch all this thing, because these are all running on basically what we call it on a run level things, kernel level stuff. So if you are doing something wrong, things will crash. So these kind of checks have been done on the build time itself. And keep going on. It is explaining your clock, and this compatible string is very, very important. That's how Zephyr know what driver to load up. So, for example, let's take some complex thing. We have what we have. Yeah, let's take this. This is good enough example. We go to drivers. Now we are touching driver layer. Since you want to know how this thing manipulated there, find in folder and paste this. Instead of underscore, it will be dash. So you see this keyword here, define DT driver compat. So that what it stands for is device tree driver compatible field, and this field will be cross reference with this particular field. You see this STM32 GPIO, STM32 GPIO. That's how when you define device tree, basically this particular line of code going to be run, and it is how this is how it's going to initialize or do whatever you want with GPIO. Pretty clear?
Yeah.
And if the status is not being set to OK on your board file, it will just ignore. So in this H7, you see tons of peripheral. But on your board file, let's say you didn't enable UART 4, UART 5, let's say, those things will just get ignored. And there are cases where when you enable UART, sometimes extra UART, there will be extra derivative clocks will be turned on. All these things are managed automatically. So that's a very good dependency checks.
So we just put what we need in that, and then only what we say will get enabled, and other things will just sit there idle.
Yeah.
So not everything gets up. It depends on the firmware that you try to load there.
So anybody that's familiar with the embedded system knows that you don't want to be too dynamic. You want to put stuff that you are using only. You don't want to keep whatever you are not using. So most of the things that happening here happens at the build time. Whatever stuffs are not being used are stripped off, whatever only needed, the device enabled only come to the firmware. That's how the block is super small. Pretty clear?
Yeah. So I just want to know if my understanding is clear. So let's say the source code is so big, and I want to do a very small application that only requires some maybe one UART, one SPI, and some other GPIOs. So when I'm like building a firmware for that, from the whole firmware, only the necessary portions are getting compiled into the firmware, and not the other unnecessary drivers or linkers or nothing will be there. So only from that it'll go down all the way to that firmware, and only, let's say I'm building for that, only those devices that I'm going to put inside will be active. Yeah. So that is how the code that happens during the build time.
Yeah.
Okay, cool.
Okay, so just to extend, so you have this since we already take a look at GPI STM32. This GPI32.c, just say you enabled one of your GPIs somehow created as well. This thing will be compiled into object basically. And just say you have time GPIOs. This thing won't be keep repeated because this thing takes a pointer as a device. And one driver thing will just keep iterating all your time GPIOs. It's very efficient. Manually, some people might not even do instance. Like a lot of projects I see, they don't build they like to repeat things. Somehow embedded engineers like to repeat things. And this solves a lot of problems. You write it once properly here, things just works out about. Any bugs here, all your device sees. You don't have all those pesties. So it's a little bit strange syntax. It's a C code, but the initialization takes 1 year, if you're curious. So there will be something called device init, basically. And you see this thing called config GPIO init priority. This is how the kernel know what at which level it should turn on. What priority is this device on, and this data is being pulled from the kconfig file. By default, all this like GPIO things are already being configured because every vendor's you want to keep it on the same kernel, which level it should turn on, what priority it is. You get the point? So every GPIO device will be on the same priority. It just comes up and looks up. And there's this concept called pre-kernel one. So pre-kernel one means before even the threads comes up, GPIO can start working. Because it is essential, sometimes you want to turn on some MOSFET power or whatsoever before thread comes. So all these things are managed for you nicely. So this is very similar to device driver model you have in Linux. You have the same concept, same abstraction bringing to microcontroller.
Good go.
So if you notice this thing actually, since we're already on the board, I'm just going to show. This is actually API mapping. This is how Zephyr maintain API between different vendors. So this truck is already being provided by Zephyr as a template, and it already being filled up with what are the APIs, pin configure, pure got and all this thing. It's mapped to vendor-based code. Every GPIO driver should have the same format. And if you take a look at this pin configure, let's do an experiment. We copy this thing. Pin con. You go to the dock. And then you go to there's something called hardware supporting reference, and we were in GPIO basically, general purpose development, and these are all the APIs, public APIs that you should, if you are doing a GPIO driver, these are the APIs you should map. So remember that earlier we saw that GPIO pin configure. This is how it works. This is a high level API. Then if you call the high level API on the back end, it will actually just go find your vendor level AI implementation. And it is abstracted among all MCs. That's how application code doesn't have to change, not dependent on any driver in the code. So if you are working on, just say UART and UART, so incidentally the driver is already there. All the APIs here you're using is called public API, which you work on all the And there are no edge cases that you can break the law. This is like a complete front looking API. And this is how you should access the device. There are some rules that you need to learn to use the Zephyr. It's a framework basically. So what I see with free RTOS or other RTOS is you don't have rules. I think that's why it's called free RTOS. I think basically you can do whatever you want. For me to taking a project from another company or working in a company, taking one project to another project, it's a big headache because people implement in their own ways. But with Zephyr, at least you have some frameworks and best practice put into. You can immediately understand the project because it's already orchestrated in a standard way. So that is what I think it's a big change.
That's good. So, how do you think? How easy it is for somebody who is doing low-level Linux operations to port to Zephyr? How good is that? Like you already talked about Linux, and I mean how the drivers and the architecture, they are all similar to Linux. So how easy it is for somebody who's completely used to Linux to get back down to this level and operate? I mean, how similar things are?
So, talking about the similarities between Zephyr and Linux, first thing is open source, so both have these common entities. Both have Linux Foundation hosted, and the style of doing things is the same. Just that this one is built on its own land because it has to run on microcontroller. But otherwise, catching up with comparing with free RTOS or whatever, you might not like free RTOS because it's too divergent. This is at least following some Linux style, like how you contribute, how drivers are layered, properly layered, and all these things. Bro, that's later.
Okay. Then we'll leave for lunch in a few minutes. So you want to conclude? Yeah.
We still take questions? Any questions from your side?
Voice have over noise. Oh, noise voice la. Okay. So
no, I think I want to show the code how we are accessing from device tree but on the source code. I think I haven't showed that code. Maybe we show that. I think that's a good concept to catch. So let's take a board for example. Okay, first I'm gonna open up a sample. Very basic sample, Blinky basically. Blinky code is open. Cool. Next next thing I'll open is the board file. I have a board file. My screen is enough font size, right?
Yeah, yeah.
Okay, let's do a code walk together.
Bro, we'll finish this and we go for lunch and then we resume. Yeah, the hands-on we do after.
Yeah, no, not hands. Just a quick one to show.
Yeah, yeah, yeah. Got it.
I think we have to do full screen. So this is basically a very basic code. What it does is in a while loop, it just keep toggling the LED on the LED. So let's see how this LED, where this data and all these parameters are coming out. The first line you see this thing, static struct the GPIO DD spec, and then you see this macro GPIO DD spec get LED0 node. See this thing? This LED0 node is coming from this defined, constant defined, and it is using another how do we call it, DT macro. It's like API, but it's a macro. That's why I said a lot of things are Zephyr do it build time rather than run time. So DT alias means it will go to your DDS and you will find something called alias code. So let's find it. So you see this alias LED0 equal to green LED. So that's how the code know. Since this is a sample, they want it to run on every board. So they have named it as a LED0. Every DTS on the board file on this Zephyr have this thing called alias. So they can map it to any name they want. And they use this macro called DT alias LED0 to identify LED0. And then after that, this is actually a structure, GPIO DT spec LED. And when you give this macro GPIO DT spec get LED0 GPIOs, it will fill up this structure actually. You know, if you have structure, you need the open curly braces and close curly braces, right? This will be done during the compile time. So this object now, the LED object, now is being accessed in C. This is like object oriented, you using C, kind of hacky way, but you know, you get GPIO is ready LED. The LED contains the LED pin number, the port and all this thing. That's how all the API understand. But you're only gonna give something called device. They call it device pointer or device simply itself. And here you can see it is GPIO configure DT. What it does, it pulls the configuration from DT file. Where was it? LED earlier. So it was saying active high. So it gets the information active file by this thing from this DD spec get. All this information is filled in this structure, and then after that you can do toggle DT. DT means device tree. It's a device tree. You are working with a device tree object. So pretty clear. Yeah.
All good, bro. We could go for lunch and we'll be back soon. So guys, we are moving for lunch and we will be back in 1 hour. We'll be back by 2 o'clock. So the stream will resume again. So thank you for watching. And I got a lot of questions also that we will be answering again. Thank you. Bye-bye.
Actually 150 will go for 130 வைக்கிறாங்க ஒரு 2 minutes